In this video lesson, we're going to go ahead and finish up the unit on thermochemistry, discussing how Hess's law works with enthalpy. Before we can discuss Hess's law and how it relates to enthalpy, it is first necessary to go over some properties of enthalpy. We've been talking all along about how enthalpy is simply heat, and in a reaction, enthalpy either increases or decreases depending on if it's exo or endo. Now, some of the things of properties of enthalpy means that we can change the reaction, in which case we'll also change the enthalpy. Notice the general rule for properties of enthalpy. It states that whatever is done to the reaction is also done to the delta H involved in the reaction. We're going to go and take a look at a few specific examples so we actually can see what this looks like. But it's important to note that this is the general idea. Now notice that states of matter must be stated because enthalpies can change depending on the state of matter. With that being said, let's look at the first property. There's two. The first property states that doubling the amounts of the reactants or products doubles the amount of the enthalpy. If you triple the amounts involved in the reaction, that will triple the enthalpy, and so on. Take a look at the example below. You'll notice that in the first reaction, you see 2H2 plus O2 yields 2H2O, the synthesis of water. Apparently, this reaction is exothermic. Specifically, it will release 483.6 kilojoules. Now take a look at the second reaction and compare it to the first reaction. Can you tell what's happened? The answer is it's been doubled. Notice the coefficients have changed from 212 to 424. According to our general rule of enthalpy, if you double the amounts of the reactants and products, you have to double the enthalpy as well. That's why the new enthalpy change is now negative 967.2. We just took the enthalpy from before and doubled it. This is the first property of enthalpy. The second property of enthalpy has to do with the actual reversing of the reaction. It states that reversing the reaction will reverse the sign of delta H. Take a look again at the examples below. We have our synthesis of water, which we know gives off 483.6 kilojoules of heat. That's why the sign is negative. However, compare the second reaction to the first. Can you tell what's happened? The answer is it's been flipped. Notice that the product 2H2O that was written in the first reaction here has now become the new reactant down here. Likewise, the reactants in the first reaction have flipped to now become the products in the second reaction. Because the reaction has been reversed, the sign of enthalpy also needs to be reversed or changed. That is why the new enthalpy in the second reaction is positive 483.6 kilojoules. These two properties together are going to help us with talking about Hess's law. Now, Hess's law states something extremely important. Let's take a moment and figure out what Hess's law states before we actually look into some examples. It looks long, but it's actually not that difficult. Hess's law states that if two or more thermochemical equations can be added together to create a net or total equation, then the enthalpy changes can also be added together to get a total enthalpy for the net reaction. If you are adding together and the products or reactants are on, the compounds are on the same side of the arrow, they can be added together. This is important to know. It's also important to know that if they are on the opposite sides of the arrow, they can be canceled out. Understanding Hess's law is important, but it's a lot easier to understand his law when we actually look at some examples. So let's do that now. What I want you to consider is the following reaction. We have 2S plus 3O2 yields 2SO3. This is the reaction that shows the synthesis of sulfur trioxide. Now a little background. Sulfur trioxide cannot be synthesized or made simply by combining sulfur and oxygen in a lab. It has to be done in steps. Notice the two equations that are below. We know the following. We know that when sulfur reacts with oxygen, it creates sulfur dioxide, in which case this reaction gives off 297 kilojoules of energy. Then what we do in the lab is we take that SO2 and we add more oxygen to it to create sulfur trioxide. This individual reaction gives us negative 198 kilojoules. What Hess's law states is that if we can find some way to add these equations to get this total reaction here, then we can also add these individual enthalpies to get this total enthalpy here. And that is what we're going to do now. On this slide, I have what was just written on the previous slide, only I've made it a little bit bigger so we have some space to work. Notice the top reaction is written in blue and the bottom reactions are written in black. I've done this so we can keep them separate. The top reaction written in blue is our total reaction. Therefore, I'm going to help make this a little easier by separating it by a line. So our goal right now is we are somehow going to manipulate or tweak these two reactions to make it look like this reaction. Once that is done, we can then add the enthalpies to get our final enthalpy. All right, I'm looking at the reaction that I want. I want 2S, 3O2, and 2SO3. Very well. I'm going to start with 2S since it's the first one. All right, according to my total reaction, I need 2 sulfurs on the reactant side. So what I do is I look down below at my 2 reactions and I try to find sulfur. Here's sulfur. Let's check if it's anywhere else. It's not O2 or SO2 or 2SO2 or O2 or 2SO3. So there's only one space actually in those 2 reactions where sulfur exists, and it's where it's underlined. Once you have found the substance that you're looking for, ask yourself 2 questions. The first question is it on the correct side of the arrow? And the second question is it the right amount? If it's not, then you need to change the reaction in order to make sure that it's yes to both those questions. So let's look at sulfur down below. We see that I have the sulfur underlined there in black. My first question, is it on the correct side of the arrow? And the answer is yes. We want the sulfur on the reactant side, or on the left side of the arrow. However, the amount is not correct. According to my total reaction on the top, I want 2 sulfurs, but down below I only have 1 sulfur. So what I'm going to do is I'm going to think to myself, all right, how do I change a coefficient of 1, which is assumed to be right here, to a 2? The answer is I have to double it, but I can't just do it to sulfur. I have to do it to everything in the reaction. And so I'm going to do that now. I'm going to multiply that by 2, that by 2, that by 2, and also my enthalpy times 2. If I take negative 297 and multiply that by 2, I end up getting that the new enthalpy is negative 594. This states the first property of enthalpy. Whatever is done to the amounts in the reaction has to be done to the enthalpy. By doing that, I now get the 2S on the reactant side, which is what I want. This is now good. All right, let's continue on. The next step in my overall reaction is the 3O2. I need 3 oxygens on the reactant side. Now let's look in our reactions below to see if we can find those oxygens. Well, here's oxygen, and here's oxygen. But oxygen is in 2 spots. How do I know which one to change? Since oxygen is in 2 places in the reactions, I'm going to skip that one for now. I always like to try to do the ones that are single rather than multiple. And so therefore, I'm going to hold off on this part in the reaction and move to the last one, which is right here. I'm looking for 2SO3 on the product side. The only spot down below where it exists is right here. All right, let's ask myself the 2 questions. Is it on the correct side of the arrow? The answer is yes. Is it the right amount? And the answer is also yes. And therefore, I don't have to do anything here. It's already where it needs to be. Now let's go back to the oxygen. This was our last step right here. We somehow need to get 3 oxygens on the reactant side. Now your initial reaction might be to look here and say, well, I don't have 3, I have 2. Therefore, something must be wrong. But remember, this was not the only oxygen. We also had oxygen down here too. Now we have 2 oxygens here on the reactant side, and we have 1 oxygen here on the reactant side. Do you remember what we do if they are on the same side? If you have the same substance on both sides of the arrow, then they can be added together. And therefore, 2 oxygens plus 1 oxygen makes a total of 3 oxygens. And that is exactly what we want. Now, what are we going to do about the leftovers? We have 2SO2 in both reactions. But notice where they are in reference to the arrow. In the first reaction, the 2SO2 was on the product side, But in the second reaction, 2SO2 is on the reactant side. Since they're on opposite sides of the arrow and they're the same amount, we're going to cancel out both of them. When you're done with this process, all the compounds down in the two reactions below should either be squared or canceled out. And they are. So we know we're done. Now that we're done manipulating the equations, we can now add our enthalpies together. The first one was negative 594, and the second one was negative 198. When you put those two things together, we end up getting a total enthalpy of negative 792 kilojoules for the overall reaction. To look at this in a little bit of a different way, notice what we did. This was the first reaction right here, and this was the second reaction right here. All we did was say, is there a way we can combine those two to get a total enthalpy? And we did, and that's how we got our total answer of negative 792. Let's go and look at a few more. All right, same deal here. I went ahead and wrote the two individual reactions in black while I kept the total reaction at the top written in blue. All right, I'm going to start out with my first substance, which is the H2. I need one of them on the reactant side. So let's look below. Where is H2? The only place H2 exists is right here. Is it on the correct side of the arrow? Yes, it is. It's on the reactant side. But do I have the correct amount? The answer is no, I don't. According to the total reaction, I only want one. But down here in this reaction, I have two. So how am I going to change the reaction below to get from 2 to 1? The answer is I need to divide everything by 2. All right, 2 divided by 2 would make this 1, and I'm going to cross that out. Oxygen is assumed to have a coefficient of 1, so 1 divided by 2 makes it 1/2, and 2 divided by 2 becomes 1 here. Remember, if you did it to the reaction, it also has to be done to the enthalpy as well. So let's not forget to do that. Negative 572 divided by 2 gives me negative 286. By doing so, I now have the H2 on my reactant side. Let's move on to the next one, H2O2. I need one of them on the reactant side. Since there's only one H2O2 in both equations below, let's go ahead and do this one now. Is it on the correct side of the arrow? The answer is no, it's not. It's on the product side that needs to be on the reactant. So this would be an example where we have to switch. All I've done here is just reverse the reaction. I made the product the reactant and the reactants the products. By flipping that, that changes the enthalpy from positive now to negative. But by doing so, I now have the H2O2 on the correct side of the arrow. And the amount is good as well. So I'm done there. The last step is I need two waters on the product side. Looking below, I see that water is written in two places. I have water right here, but I also have water right there. Notice which sides of the arrows they're on. This water right here is written on the product side. This water is also written on the product side. And since they're written on the same side of the arrow, they can be added together. Therefore, one water plus one water gives us the two waters that we want. Now, what are we going to do with those leftovers? Notice this half oxygen is on the product side, whereas this half oxygen is on the reactant side. Since they're the same amounts and the same substance on opposite sides, they can be canceled out. Now everything has been manipulated to match the reaction above. So now our enthalpies are ready to add together. Negative 87.3 and negative 286 added together gives us a total enthalpy change of negative 373.3 kilojoules. That is the total enthalpy change for the total reaction. Let's go ahead and do one more together. This will be our last example for Hess's law. Notice that I have the equations written. The equation on the top written in blue is our total equation. This is the equation we're trying to calculate the total enthalpy for. Now that total equation comes from the two equations written below in black. The first one has an enthalpy change of negative 206, while the second one has an enthalpy change of negative 136. Let's go ahead and start manipulating to get the bottom two reactions to look like the top one. All right, I'm looking for a CuCl2 on the reactant side and just one of them. Here is the CuCl2, and I have one of them, but it's written on the wrong side. So what I'm going to do is I'm going to flip this reaction. I'm going to rewrite it above. CuCl2 yields Cu plus Cl2. By reversing the reaction, that reverses the sign of enthalpy. It now is positive 206. Now, anytime I change a reaction, I usually like to get in the habit of erasing things that I'm done with. And therefore, this reaction right here, since it was already flipped, I'm going to get rid of. All right, now I have the new reaction flipped exactly where I want it. And the CuCl2 is on the correct side. The next substance in the total equation is the 1 copper on the reactant side. But notice, copper is written in two areas, right here and right here. So I'm going to skip that and leave that till the end because there's doubles. Let's move on to the final one, the 2CuCl. I know there's only one place in the reactions down below where that exists, and that's right here. Is it on the correct side of the arrow? Yes, it is. It needs to be on the product side. Do we have the correct amount? The answer, once again, is yes. We need it too. And so we're already done there. The final step now is to look at our copper. We somehow need to get 1 copper on our reactant side. Now your temptation might be to look at this copper right here and say, well, we have 1 copper, but it's on the wrong side. This reaction needs to be flipped. That's, however, incorrect because if you flip the reaction, you will undo what you did with this compound right here. And we don't want to do that. Therefore, there must be something there that we don't see. And so let's take a look if there's more coppers. And there is. There's another copper down here. In fact, there's 2 of them. So we have 1 copper up here on the product side and 2 coppers down here on the reactant side. They're on opposite sides, and so they're going to cross out. But they're not both going to cross out completely because the amounts are different. There's 1 in the first reaction and 2 in the second reaction. Therefore, this copper would cancel out altogether. But in this copper down here, there would be some leftovers. One of them would go away, and so you'd be left with 1 copper left over. And notice, that's what we want. We want 1 copper on the reactant side. So it automatically cancels out on its own. The remainder, the Cl2s, those get canceled out. This one on the product side, this one on the reactant side. Now everything is boxed or circled or crossed out, and now all we have to do is add the enthalpies together. Positive 206 and negative 136 together gives us a total enthalpy change of 70 kilojoules. This lesson concludes Hess's law.